We now want to start our discussion on rotational motion and objects moving rotationally as opposed to linearly. Okay, so we're going to restrict our discussion to objects that are moving around the rim of a circle. And let's just say that we have an initial point on our circle, and we'll call it xi for lack of a better variable. We don't necessarily want to use x's and y's here, but you'll see why in a moment that we just need a generic variable here for the time being, and then we'll define the variable that we want to use. And let's say that our circle starts to rotate, right? And so after some time, my point has moved through this angle theta, and it is now up here. And angles are always defined as positive from the x-axis. So if this is the positive x-axis and this is the positive y-axis, then angles are always going to be measured as positive from those points. And so we now have a decision to make, right? I can either try and keep track of the x and y positions at my initial and final points, or I can just keep track of one coordinate. And we're moving in 2 dimensions, so how does that work? Well, if we were restricting ourselves to the circumference of a circle, then the distance from the circle is always going to stay the same. So I can now start to talk about points in terms of r's and thetas instead of x's and y's. And the reason that this allows me to simplify my notation is my initial point and my final point in Cartesian coordinates are going to be coordinates of both x and y. Whereas now, if my radial position remains constant, I'm only worried about the angle that my object moves through. So now my position coordinate can be taken or replaced by just the angle theta. If I know what r is and I know what theta is, then I know 2 things about my coordinate which allows me to uniquely specify its position just as if I knew its x and its y coordinate. Right? But if if r is constant, then theta is the only thing that's changing. Right? Now, for any given circle, we have a general relationship. If I look at the distance along the circumference that my particle moves through from here to here, the distance along the circumference, we call that the arc length, and it's denoted by the symbol s. All right? So this is the arc length, s. And we have this specific relationship that the angle theta is equal to the arc length divided by the radius. All right? And that is a general result from geometry for circles. All right? And we now need to look at how the angle is going to be changing in time. If my circle is just rotating at a uniform rate, then one of the quantities of interest is going to be how is that angle changing with respect to time? What is d theta dt? And so, well, let's start out with delta theta. So what is delta theta delta t? That is the amount of angle that my wheel or rotating object or whatever it is has gone through in some amount of time t. That is the same thing as what we call the angular velocity. Okay, so the angular velocity is just the number of angles per unit time, or the amount of angle per unit time that a rotating object moves through. Okay, it's the amount of angle per time. And I do need to stress, and I cannot stress this enough, the rotational quantities that we're going to introduce, theta, omega, and alpha, the angular units in those quantities are going to be measured in radians and not degrees. Okay, radians and not degrees. All right, so the angular velocity, the amount of angle that an object moves through as it is rotating, we call that the angular velocity. Okay, so omega, and it's not a W, it's the Greek letter omega, is the angular velocity. Okay. This is the angular velocity. Likewise, if the object is increasing its angular velocity, it is experiencing an angular acceleration. Okay? So we can also have angular acceleration, and as you might guess, angular acceleration, we denote it by the Greek letter alpha, and it is going to be given by the change in the angular velocity with respect to time. So the angular velocity is just the amount of radians per unit time, usually per seconds, radians per seconds, that my object is moving through, and then if I'm speeding up, that rate is going to be increased, and that rate is the time rate of change of the angular velocity. And if I consider infinitely small time intervals, then these delta t's will get moved to dt's, and these will get moved to differentials. So in the calculus way of thinking, the angular velocity is d theta dt, and the angular acceleration is d omega dt. And likewise with linear acceleration, we had linear acceleration is equal to dv dt, or d squared x dt squared. This is also likewise d squared theta dt squared. Okay, so angular acceleration is also likewise d squared theta dt squared. All right, now here's a question. Let's suppose I have a bike tire, and that bike tire is rotating at a uniform angular speed. So omega is constant for this bike tire. And I put the bike tire on the road or on the ground or whatever, and it starts rolling forward. How is the speed that it is rolling forward with related to the rate at which it's spinning? And of course, the two are going to be related. We can visualize that very clearly. The faster my wheel is going to be rotating, the faster it's going to be moving down the ground or across the ground. And you know this from experience if you've ever ridden a bike. The harder you pedal, the faster you're making your tires go. The faster you make your tires go, the faster you're propelled forward. But what is the actual relationship between that speed angularly and the linear speed that is the object's moving forward with? Well, let's come back to this equation here, and let me say that S is equal to r theta, all right? And remember, S is the distance along the arc. It's the arc length. And now if I differentiate both sides with respect to time, r is constant, so it does not get differentiated. And we have that ds dt is equal to r d theta dt, or r d theta dt is the same thing as r omega. So d theta dt is the same thing as r omega. And ds dt, all right, if you look at infinitely small time intervals here, right, very, very tiny time intervals, then your arc length S, the infinitesimally small arc length, is not going to really change direction. And so this is the linear velocity that the object is experiencing. So over these infinitely small time intervals, we can claim that ds dt is equal to v. And so the linear speed v that a bike tire is moving forward with is going to be equal to the angular rate of motion, its angular velocity, times its radius. And that should also make some sense. The smaller my radius, the slower my object is going to go. If I have two objects that are, one is much bigger than another one, then, and they're both spinning at the same rate, then the larger object is going to be moving faster. It's going to be covering a larger amount of ground. Likewise, a very large radius is going to cause faster motion if I have two objects that are spinning at the same rate. And likewise, if I have two objects that are the same size, obviously the one with the higher rate of angular velocity is going to be moving faster. Just like we can differentiate this equation with respect to time, we can differentiate this equation with respect to time to get a relationship between linear acceleration and angular acceleration. And if I differentiate this, well, dv dt is acceleration, linear acceleration. If r is constant, it does not get differentiated, and d omega dt is alpha. So likewise, if I'm speeding up or slowing down angularly, then that's also going to correlate with a linear acceleration or deceleration. Okay, so remember these two formulas because these give us a bridge between linear variables and angular variables. Now, one more thing before we're done, I want to give you guys some relationships and kinematic equations in the rotational cases. Now remember that we derived a set of kinematic equations in the linear case, right? So if we just look at linear, remember that we had, we defined displacement as delta x, we defined velocity as delta x, delta t, or letting our time intervals become infinitely small. And from these, we were able to build our sets of kinematic equations, which included and so we have these sets of kinematic equations. And we can actually build analogous kinematic equations for the rotational case if everywhere that there's an x, we replace it with theta. Everywhere there's a v, we replace it with omega. And everywhere there's an a, we replace that with alpha. So our rotational kinematic equations are going to look like this. Our displacement is going to be angularly, and it's going to be delta theta. Our velocity is going to be omega is equal to d theta dt. Alpha is equal to d omega dt. And now, so we have Vf equals Vi plus At. We can write this in the rotational case as omega f equals omega I plus alpha t. We're going to have delta theta is equal to omega I t plus 1/2 alpha t squared. And we're going to have omega f, omega f squared equals omega I squared plus 2 alpha delta theta. All right, so these kinematic equations we can now use to solve rotational cases, and that's what we're going to do in the next video.